And on page 69, it says study the example, underline 2 parts that you think make it a particularly good answer and a helpful example. An object traveling at the speed of sound at sea level travels about 20 kilometers in 1 minute. Write equations that can be used to find the following: the distance when given the time and the time when given the distance. So we're writing 2 equations using the same information, which just means we're going to be in 2 different forms. They will be equivalent in just different forms. Use a table, graph, or diagram to show the 2 relationships and then describe the relationships. Explain whether or not the relationships are function. Show your work. They're telling you everything to do. The reason they work this out is so when you do one on your own on the next page, you know what to make yours look like. Possible answer: let D equal the distance and T equal the time. An equation for the distance would be D is the distance is equal to that rate they gave us, which was 20 kilometers per minute, times the time, or the number of minutes. Remember, distance is equal to rate times time. And an equation for the time given the distance, you would solve for T instead of D, and you would do that by dividing by 20, giving you T is equal to 1 over 20 D. It's just like that other example that had a equivalent equation. Okay, 2 different forms of the same equation should be equivalent. Now they chose a mapping diagram for their data. Their input was 1 through 5 minutes. And their output was their distance, 20, 40, 60, 80, 100, and then they paired those up. For the other equation, their inputs is the distance, 20, 40, 60, 80, 100, and their output would be the time that they was traveling. And then, of course, they got 1 through 5. Connect those with a single line, and that's it. Then they had to explain the distance is 20 times the time, and the time is 1/20th of the distance. You're just describing your equation in words. In both relationships, there is only one possible output for each input, so both are functions. Okay, easy stuff. Now on the back of this page, they wanted you to do one of these for yourself. They give you an example. Each molecule of carbon dioxide contains 2 oxygen atoms and 1 carbon atom. Write equations that can be used to find the following: the number of oxygen atoms when given the number of carbon atoms, and the number of carbon atoms when given the number of oxygen atoms. So in the first equation, we want oxygen equal to a rate or a constant of proportionality when given carbon. So we want oxygen based on carbon. And the second equation, we want the opposite of that. We want carbon based on oxygen. We just need a ratio for those and the equations will be done. Each molecule of carbon dioxide is 2 oxygen atoms per 1 carbon. That's 2 oxygen per 1 carbon. Now, if we want to find out how many oxygen atoms there are, we're going to multiply the number of carbon atoms by 2. Okay, 2 oxygens for each carbon. When we multiply, it will give us oxygen. Now, if we're going to do it the other way, we would be solving for C instead of O. If we wanted to rewrite this equation, we would have oxygen is equal to 2 times carbon. If we divide by 2, we would get C is equal to 1/2 the oxygen atoms. Okay, O is probably not the best variable there, just so you know. Now, they want us to use a table, a diagram, or a graph to show the 2 relationships and then describe the relationships and explain whether or not the relationships are functions. They did mapping diagrams on the last page. You could do mapping diagrams. You could do tables. Let me show you a table. So if we did oxygen as the input and carbon as the output, I could say 1, 2, 3, 4, 5 oxygen atoms. And then we could use our formula, oxygen, we would want carbon, we're solving for carbon. So 1/2 times the number of oxygen. So 1/2 of 1 would be 1/2 or 0.5, I'll give you both. And then 1/2 of 2 would be 1. 1/2 of 3 would be 3/2, or 1.5. 4 would be 2, and then 5 would be 5/2, or 2.5. So you could do it as a table. You could also make it a graph. I'll put oxygen down here and carbon up here. And then let's do 1, 2, 3, 4, 5. And then up my carbon, I need to go all the way up to 2.5. So maybe I'll just go 1, 2, 3. And then I could plot my points. 1 oxygen atom was 1/2 carbon. 2 oxygens was 1. 3 was 1.5. 4 was 2. And 2. And that would be a graph. This was the one for carbon is equal to 1/2 of oxygen. For the other one, we was using carbon as the input and oxygen as the output, so you could make a quick table there. Carbons, 1, 2, 3, 4, 5, and then we have to double the carbon atoms for oxygen, so 2 times 1 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, and 5 times 2 is 10. We could also graph it. This time carbon goes on the bottom and oxygen goes on the side. Carbon, we went 1 through 5, 3, 4, 5, 1, 2, 3, 4, 5, and we need to go all the way to 10. So I'm going to go 2, 4, 6, 8, 10. Or you could just go by ones. It's totally fine. And then you would just graph them. 1 was 2, 2 was 4, 3 was 6, 4 was 8, and 5 was 10. And this was oxygen is equal to 2 times carbon. The last thing you had to do was describe the relationship. Carbon atoms is equal to 1/2 of the oxygen atoms, or oxygen is equal to 2 times the carbon atoms. Okay, I'm not going to write that down. And then you had to tell if it's a function. We only had one of each input, which makes it a function, or you can look at your graphs. They pass the vertical line test, so they are both functions. Okay, they are both functions.